Okay, this is going on page 91 when we're done. All right, so we're going to talk about linear and angular speed. What's another word for linear and angular speed? Instead of speed, we could say velocity, okay? And this is something that you should have talked about in physics. Most likely, whether you're in on-level or AP, you should have talked about it. Maybe not by now. I don't know what it is in the curriculum. I'm pretty sure in AP, though, you've already done it. But it may not look exactly like this. So we need to talk a little bit about the difference between the linear speed and the angular speed that's happening. And so I'm going to show you a really, really short YouTube video, and it's like the worst YouTube video I've ever made. And I'm going to have to turn out all the lights so you can even see it. But it gets the point across, okay? And so I'll put it up here, and then I will explain to you why it's important to see. But I don't even know why somebody would, they needed to turn the lights on wherever they were doing this. But, okay, so before I hit play, it's just a turntable, and there's two little Lego guys, right? And so as they spin on this turntable, you don't even need sound because there isn't any, but I want you to see that one of them is moving faster than the other as far as linear speed is concerned. Does that make sense? However, their angular speed is the same because they are making the same amount of, well, I guess I didn't have it on replay. They didn't have it on the same, they have the same amount of rotations per minute, right? They're one rotation. It's like if we were running around the track and one of us is on the inside of the track and one of them is on the outside, right? The outside person is having to run farther to make one loop around. But we could still make we could end up back at the beginning every time together. So just know that the outside person's having to move faster to keep up. So the linear speed is different because however many inches per minute they're moving, he's moving a faster rate. But when you're talking about the degrees or radians per minute, the actual revolutions, that's the same. Does that make sense to you? So you're measuring different things. You're measuring the revolutions or you're measuring the actual distance. And it's possible to have the same angular velocity but a different linear velocity. Does that make sense to you? So I want to make sure you understand how they're different. All right, so how do I get out of this? All right, I know that was a pretty bad video, but it gets the point across pretty well. But yeah, all right, so. Well, I didn't mean bad but just the quality. If they had just turned the lights on, it would probably been a lot better. So arc length can be used to analyze circular motion. Suppose that an object moves along a circular path S with radius r. So particle or whatever it is, you'll talk a lot about particles moving when you get into calculus. This particle moves left and right and whatever. So you have something, it's a little here and it's going to move along this path. We can talk about this as far as an angle measure, the amount of revolutions that it goes. Okay, so at the rate at which the object moves along the path is called the linear speed. Okay, so your linear speed is like your distance or your velocity. So v is velocity, and it's just equal to s t, and both lowercase. What does s represent that we just did? No, velocity is the speed. Arc length, yes. This is arc length over time. That makes sense, right? That's what your velocity is. It's distance over time, right? And your arc length here is just your distance. Miles per hour, whatever. It's your velocity. Your angular speed, now when you write this, it's a lowercase w, but it's a lowercase cursive, not really even cursive. It's like a puffed up W. It's actually a Greek letter. It's not a W. Do you know which one it is? Find your, what page is your Greek alphabet on? Look up your Greek alphabet. It's in bright green paper, I think.
Hey, I know it.
And it's your lowercase, but did y'all not talk about it in physics? Yeah. When you did did you do angular speed or just linear speed? Do you remember? Okay. So it is if you find the Greek alphabet, it is this little W, which is not really a W. This is the Greek letter omega. So omega represents the angular speed, and all that is your angle over time. Okay, and this is the central angle. Okay, easy enough? All right. So let's look at what's happening here. It says, used for questions 1 and 2, a bicycle tire with a radius of 14 inches rotates at a rate of 125 revolutions per minute. We want to find the linear speed of the tire in inches per minute. Now, your units are very important here. So we're going to have to make sure that we convert correctly, but we'll be able to use the calculator to help us with those things as we go through here. So our formula is that we're going to use to find the, what is this first? Linear speed. The velocity is equal to the arc length over time, right? That means I have to find the arc length. What's your arc length formula? We did it yesterday. Okay. Okay, it does come from the circumference. The circumference is all the way around, right? And it's 2 pi r. So it's not the 1/2 pi r. That, remember, just think about 2 pi r is circumference. 2 pi r is all the way around. We're not necessarily going all the way around. So there's r theta. The theta is not 2 pi, so it's r theta. So r theta is super, that's it, r theta. That's the arc length, okay? So do we know the radius here? Yes, okay. Is, yes, 14 inches. Okay, so now your theta. Do we know that? No, but it gives us 125 revolutions per minute, right? So 1 revolution is how many radians? 2 pi. So 1 revolution is equal to 2 pi radians. Does that make sense to you? 1 time around, that's my angle measure. So in order to find your theta, you just take 2 pi times the number of revolutions, whatever it happens to be. That's how you get the angle, okay? So since we have that, and we can do it all in one piece, we don't have to split it up necessarily, but this theta that's here is going to be 2 pi times the number of revolutions, which is 125 for every minute. Does that make sense to you? So now we can type all that in the calculator. And we're going to give it an exact, we're going to leave it in exact form right now. Leave it in terms of pi. So hit your SD key again.
250 pi.
You're not stupid. You found just this part. I would go ahead and give me the whole thing. Yeah, okay. Does that make sense? Good. 3,500 pi. Now let's talk about units, because look, overall, y'all are sloppy with units. You don't think they're important. They are hugely important. And they're important before the very end of the problem, too. We're not finished with the problem. This is arc length, and it's asking me for linear speed. But I have to know what my units are right now. What are they right now? But it's just arc length, so it is what? Inches. Does that make sense to you? So right now, we just have, my arc length is this many inches. Now, the next part of this is going to seem a little silly at first, but I promise you there's a reason for this, because it's not always going to work out quite as nicely. The velocity that we're actually looking for is the arc length, which is what we have, this 3,500 pi, divided by time. Now, the time that we have, since we use this 125, and that was revolutions per minute, so I do 125 times per minute. The time I have has to be 1 minute. So this, when I write this out, this is 3,500 pi inches over 1 minute. Okay. So when all is said and done, since that was 1 minute, I'm dividing by 1, which means I'm not really dividing anything. And so my final answer is 3,500 pi inches per minute. Okay, and this is my answer. Everybody okay with that?
So if we would have did the revolutions in seconds, then we would have to multiply by, divided by 60?
Yes, or what I would suggest instead, his question was if that had been like revolutions per second and we wanted it in minutes, then we'd have to divide by 60. But what I suggest to you in doing is not just dividing by 60 or multiplying by 60, because a lot of times we get those things backwards, is setting it up in inches per second, and then once it's set up, then you convert. And that's what we're going to do. It's way safer, because otherwise y'all do things backwards because you try and blow through it and you're not thinking about it correctly. So, all right, let's look at number 2. It says, and we're doing, find the angular speed of the tire in radians per minute. So my angular speed is omega. It's equal to what over what? Theta over time. Did we already find theta? Yes, sort of. Like, we didn't really find it. We put it in here, but since we have it, and somebody did give me the answer. The theta I get, because it's 2 pi times 125, it is 250 pi. You'll agree with that and see where it's coming from? So then my omega here, this is 250 pi radians for every 1 minute. So this is 250 pi radians per minute. And I know, because I know what you're thinking, and that's not miles, it's minutes, but I ran out of room and I can't write any closer to the thing. Like, why do I have to write it like this if it's going to be this in the end? Because it's not always just going to be this in the end. Sometimes we're going to have to convert. And the other part of that is I want you to understand when you're having to convert, or when you have a rate of some sort or units that are in a fractional form, how to go backwards. Like if I have 3,500 inches per minute, or it's a fraction or whatever, all this really means is you can basically straighten that back up. Put that over 1, and then the numerator goes with the numerator in there, and the denominator goes with the denominator there, and you have this set up, which is going to be way better for you to do when you actually convert. Okay? Does that make sense to you? All right. So let's see. We're going to, we will skip. No, I don't think we need to do 3 and, well, do you want to do 3 and 4? I'd rather get to ones where we have to convert. Let's skip. We're going to skip to 5 because I'm afraid we're going to run out of room towards the end. We're the same type of problem, and we'll do other ones with it. It's fine. Because let me just double check that. Because, why? Because I just ignored what you said? Oh, and I was like, no. Were you being serious? Do you really want to do them? I didn't think. I knew better. All right, so number 5. A 16-inch diameter tire on a car is making 500 revolutions per minute. Find the linear speed of the tire in miles per hour. So we're going to start the exact same way, right? We start that we're going to have to find the velocity, so we're going to need the arc length first. So we're going to find the arc length. What's the radius? 8. Okay, and then your theta is 2 pi times the revolutions, which are what? 500. Okay? Everybody understand where those numbers are coming from? Like, there's only 2 things in my formula, but I'm writing 3 things down. That's because the 2 things give me my theta. Okay? So then you can type that into your calculator, and, oh, I'm looking at the wrong thing. You get out 8,000 pi inches. Yes, good. So this is 8,000 pi inches. So now to go substitute this in for velocity, my velocity is just my arc length divided by time, right? So my arc length is 8,000 pi inches over, and then this was revolutions per minute, so this is over 1 minute. Okay. So am I just done and it's 8,000 revolutions per minute? No. Or inches per minute, I'm sorry? No, I'm not, because it asks me for this in miles per hour. Okay, so you need to do this in a very logical, structured form, and it's easy and you won't mess it up. I know y'all hate this stuff. This is what I hear every time I do this because you had to do this so much in chemistry and I think in physics too. But here's how you make it easy on yourself. I need to change. I'm just going to start with the numerator. We'll get to the hours in a minute, but let's talk about inches. I need to change the inches into miles. Well, I don't want to go directly to miles because I don't even know what that conversion is. I can go from inches to feet. So I know if I want inches to cancel out, my inches have to be in the denominator so they cancel out, right? And I'm going to go from inches to feet. Well, how many inches are in a foot? 12. So 12 goes here, 1 goes here. I don't want feet. I need miles, right? You should know how many feet are in a mile. If you don't, that's something you have to know. 5,280. So this feet has to cancel out. Listen. So again, it goes in the denominator, so it cancels out. Miles are in the numerator. 1 mile is 5,280 feet. Okay, so now I've got, what did I do wrong? Oh, no, that's right. Had that moment again. So I'm good for miles so far. I'm just not finished. I just had that bad feeling I did something wrong there. So I'm good. I got miles, but now I got to do hours. So I just keep going here because we got a calculator. We'll put all this in. I need to change the minutes to hours. Okay, well, minutes have to go in the numerator so that they'll cancel out with the denominator. I can go from minutes to hours, right? How many minutes are an hour? 60. So I put 60 here and 1 here. So now, and just pause for a second before you start typing buttons in, or typing things in. I want you to understand, you need to be capable of doing this without a calculator, okay? So you need to be able to reduce. We're not going to do that right now because we don't have time. I just want you to understand that this is a fair question to be a non-calculator question. And so you want to go through and logically kind of reduce. I would totally not multiply straight across and reduce the fractions. That's yucky, right? But if you have a calculator, you can type them in. I would highly suggest when you're using these to actually type them all in as fractions and then just multiply them all together, okay? Because that's what's happening here. So on your calculator, we can do 8,000, and I'm going to leave the pi. I know in the end pi goes on the end, but I don't want to have to mess with it. So I'm going to make a fraction. I'm going to do 8,000 over 1. And really, if it's over 1, you could leave that off, but it doesn't matter. I'm going to do it so it looks exactly the same, so I can double check myself. 1 over 12 times 1 over 5,280 times 60 over 1. Okay, so here is, you can't even see that. I've lost my document camera completely. So this is exactly what's on my paper, and I can arrow to the left if I need to see, what's going on over there. I can see it all there. Okay, so then I just hit equals, and it takes care of all of it for me. I just have to remember to put the pi back in there. If you're afraid that you're going to leave it off and you're using this calculator, you can type it in there and it'll leave it exact for you. So what we get here then is the velocity is 250 pi over 33, and that is miles per hour. You're getting to use the calculator to help you with the numbers, but if you do not, and what's the name for this? I never can remember, but you call it something different in science. Like this conversion, the way you're doing it, it's called, I never can think of it. No. Dimensional analysis, that's what it is. I don't know why I can never remember those words. Because as soon as I start doing this, people are like, oh, it's dimensional analysis. I don't know why you hate it so much, because it's really not that bad. If you line everything up and understand how it's supposed to cancel out, it's not a problem. Well, and you have to know the conversions, yeah. Okay, so let's look at the back. We are going to do, let's see. Let me see. I'm going to have you do number 6. A circular saw blade with a diameter of 9 inches. Mine will change in just a minute, I'm hoping. Oh, there we go. Nope. Did I not cancel this out? What is going on with my board? All right, just do, oh, I didn't clear it off, that's why. Oh my gosh, this board. It may not be right. Oh, I know it's recording. Okay. So go ahead and, well, let's do number 6 together because we skipped 3 and 4. So this is a circular saw blade with a diameter of 9 inches, rotates 2,800 revolutions per minute. Find the angular speed of the blade in radians per second. Okay, so angular speed, or the angular velocity, that's when we use omega. Okay? So omega is equal to theta over time. So I need to find theta, and it gives me the diameter. Do I even end up using that? No. I find theta by doing, theta is equal to 2 pi times the revolutions, which are 2,800. Okay, and so when I multiply that, what do I get for theta? (5,600 pi). Okay, and this is my radians. Yes? Okay, so now to find omega, it's your theta over time. So this is 5,600 pi radians for every one, what was it? Revolutions per minute. What I need is find the angular speed, the blade in radians per second. So go ahead and finish up that conversion. Write it out. Like, do your little dimensional analysis. Maybe if I say it a few times, I'll remember the words. Okay, so we're good with the radians, right? Because we want it in radians per second. I need my minutes to cancel out, so they have to go in the numerator. Seconds go in the denominator. So where does 60 go, numerator or denominator over here? Denominator. Now, when you have done this and haven't written it out like this, you just go, oh, I multiply by 60, or oh, I divide by 60. Have you ever done it backwards? Multiply when you're supposed to divide, or vice versa? Maybe not. For most people, that's at least once. Yes, that has happened. So it's this way you know for sure what's happening because you're looking at your units. Because units are huge, and getting them correct. It's a big, big deal if they're not right. So plus it would make your number wrong. So then when you let the calculator help you with this, what do we get in the end? Good. So 280 pi over 3, and this is radians per second. We good? All right, so I want you to work number 7. Number 7, and that is linear speed, which means it's very, very similar to number 5 on the front. But you got some conversions to do there. Well, I wouldn't say it's really big. What do you have? No. That's your final answer? I wouldn't start typing anything until you have all of this. Oh, I'm so sorry. I just threw my pen. Do it right. I would until you have it all written out. Make sure your units are canceling out and all that good kind of stuff. Okay. No, it says miles per hour, and that's not radians. You don't have units on there either. That's why you're confused. So your very first step for velocity should be feet per second. Do we all agree with that at least? Okay, then keep going. I just want to make sure you understand because this, since this says revolutions per second, that's how that started with seconds. Okay. All right, good. Then keep going. Once you get your answer, let me know and I will come check it. We're close, but no cigar. And the miles per hour. Good job. Yes. You did it. Good job. And if you're stuck, let me know. Don't just try and hide your paper when I come over and look. I know. I'm hip to your game. We doing okay? It is not that. I think you were probably missing something in your conversion. So I'm not gonna write out the answer here. I'm just gonna write out how many blanks it took me. I had to do it 3 times. Okay. Okay. So. Because what I want is miles per hour. So if I just look at units, which, you know, depending on how you go about this might help, you know, if units are what's hurting you, then just start with that. I need the seconds to cancel out, and I can go from seconds to minutes. But I don't want minutes, I want hours, right? So then I need minutes up here. So there's hours down here, so those cancel out. So I've got hours there, that's good. But then I need miles per hour, so the feet have to cancel out. And I can change that to miles, and then my units would be good. So if you can plug in the numbers that go there and then put it in the calculator, you're good to go. If you did all that, then you might have hit a wrong button. That's very possible. I don't have to check it. Well, yes, I have to check yours. There you go. But that pi needs to be in the numerator. Okay, good. Did you? So. Did you put do your numbers look like mine? Oh. Okay. Yeah, it helps when you use the right numbers. It usually helps you get the right answer. Okay. All right, so in the end, we get 1,050 pi over 11, and that is in miles per hour. You did something wrong. Did you find it? That's very possible. Do your fractions look like mine? Yeah, you did yours in a different order, which is fine. If you did the miles first, that's absolutely fine. Like that doesn't matter. So all of the numbers you have written down is correct. Oh, look, you used 5,250 because you can't read your own handwriting, and that probably had something to do with it. Are we good? Ask me questions if you got questions. I'm sorry. You don't appreciate it. Are you good? Yes? All right, so let's look at this. Now, I'm going to show you this part here, and this is, you can look at it one of two ways. Either a different way to do exactly what we just did, but it's really not even that different, or it's good to know in case you're given different information. But instead of basically waiting until the end and doing the conversions all at once, you kind of do part of the conversions and then the other part. And it's a personal preference. I think you really just need to know that it's possible to do it both ways and how things work together. So we're going to kind of develop it here. We've got the velocity we know is, what's our little formula for that? What are we using? S over t. Okay, so then what we've been doing is going and finding S, right? What's your formula for S? R theta, right? So that's really R theta over t. Would you agree with that? So now I'm going to kind of factor the r out, so I get r times theta over t. Well, what is theta over t? Look on the front. What's that formula? Theta over t. That's your angular speed, right? It's your omega. So this is really then r times omega, right? So another way to look at velocity besides s over t, velocity is also equal to the radius times the angular speed. You get the same answer either way. But if I tell you what the angular speed is, then you can just multiply by the radius and bam, there's your velocity, okay? Because you get the same answer either way. But let's look at why this might be a little bit different way to work it. It says a ceiling fan with 25-inch blades, so again, that is the radius, rotates at 40 RPM. That's revolutions per what? Minutes. Always revolutions per minute for RPM. Find the linear speed of the tips of the blades in feet per second. So what we're going to do is we're going to start by finding angular velocity. So our angular velocity is theta over time. Right? So we find theta by taking 2 pi and multiplying it by the revolutions, which are 40, over time, which is, it's revolutions per minute, so this is 1 minute. Okay? And this is going to be radians, so we'll get radians per minute. So this gives me 2 pi, not 2 pi, duh. When I multiply it, what do I actually get? Sorry, yeah, 80 pi. Now I have to, my board is taking forever. 80 pi, and we'll have radians per minute. Now, I can do one of two things. I can leave it like that and substitute it in, or I can go ahead and do some of the conversions right now. So just for the heck of it, to be a little bit different, we'll do some of them right now. So I have 80 pi radians per minute. My end goal, what I want is the linear speed, which I haven't even looked at yet, but I want it in feet per second. So I'm going to take care of the seconds right now. which means I can multiply this, cancel my minutes out, convert it to seconds. So there's 1 minute for every 60 seconds. And then when I do that, what does that give me as a fraction here? You have a calculator. 4 pi over 3. Yeah, 4 pi thirds. And this is radians per second. Make sense? Okay, so now I have it in seconds. That's good. So now we're going to go and substitute it in to find the actual velocity, which in this case is r times omega instead of theta over t, because I already basically have the time calculated in there. What's the radius? 25. So I'm going to get 25 times 4 pi thirds. Right? So I'm multiplying something that's not a fraction by something that is. So I'm going to put this over 1, and I'm not going to actually multiply yet. And we know it's 100, but it's fine. We're not necessarily going to worry about it just yet. Actually, we are. We'll go ahead and do that. We'll get 100 pi over 3, and that 25 was in inches, right? And it was inches per second. So you basically go 100 pi inches in every 3 seconds. I don't want it in inches. What do I want it in? Feet. So now I convert that. Inches here, feet here. So 1 foot for every 12 inches. That cancels out. Then I can just multiply straight across. Let the calculator do the work for you here. And you should get 25 pi over 9 feet per second. You're doing the same work, just maybe in a different order, or but it's the same thing, and both of them work. The only reason you really kind of have to know both of them, or I would make you do one and not the other, is if there's multiple choice questions, and they can ask them in such a way that if you don't know there's 2 different ways to do it, you won't have a clue what's going on. So you at least need to be familiar with both, but you can work them however you want. Okay? I personally like what's on the front a little bit better, but that's just me. Okay? Any questions? We good? Where's the homework? I'm going to give it to you. All right, so go ahead and tape this in.